All right, so we are going to talk about trigonometry and calculus all in the same breath. We're going to blend these two ideas, and we're going to look at a number of examples where we're taking derivatives of trigonometric functions. But first, we need to develop these ideas. I'm going to split this into a series of 4 shorter videos so that it makes it a little bit easier to digest. But first, what we need to look at is an important limit, and actually we're going to look at 2 important limits, the first of which is the limit as h goes to 0 of sine h over h. And let's be clear that when we're talking about the sine of h, we are talking about an angle in radians. When we use calculus and trigonometry, the angle measurements are always going to be in radians. I shouldn't say always, but almost always. So, what is this? To understand that question, I have a circle over here, and we're going to consider a couple things. If I draw an angle, like so, and that's h radians, what I know is that that height would be the sine of h. We know that from our unit circle using trigonometry. And I'm not sure if you're aware of this or not, but there's a physical definition of what tangent is also. If I draw a tangent line where the circle meets the x-axis, the length of that tangent segment going up to the angle, that length is actually the tangent of angle h. And this angle has cut an arc, and that arc has length of h. So what is the relationship between h, sine of h, and tangent h? Well, we can write a compound inequality and say that h is less than or equal to tangent h. That always has to be true. And h also has to be greater than or equal to sine h. And now we're going to look at a couple manipulations, some algebraic work. I'm going to divide each piece of this by sine of h. What we end up with is that 1 is less than or equal to h over sine h, less than or equal to tangent h. It would be tangent h divided by sine h, but we know that if we simplify that, since tangent is sine over cosine, this becomes 1 over cosine h. Now, it's legal to divide by sine of h because we're going to be looking at what happens as h approaches 0, not what happens when h is 0. So we don't have to worry about dividing by 0 in this case. And I'm going to take the reciprocal of all these things. And in doing that, the order of the inequality is going to turn around. Now, 1 is the largest thing. Sine h over h is still in the middle, and cosine h has to be less than or equal to 1. We know that. Cosine of h can't be greater than 1. And now, what happens as we take the limit? Limit h approaches 0, and we're going to go from the positive side right now. If we take the limit of all these things, as h approaches 0 from the positive, the inequality should still be preserved. And let's look at what this becomes. As we approach 0 from the positive side, as we get closer and closer and closer to 0 coming from the right on the number line, cosine gets closer and closer to 0, so that this first limit right there, that's equal to 1. And the limit of 1 as h goes to anything, that's always 1. And since the limit of sine h over h as h approaches 0 from the positive is it less than or equal to 1 and greater than or equal to 1, we know that the limit as h approaches 0 of sine h over h has to be 1. It's sandwiched in between there. It's squeezed in between. But what about from the other side? We actually don't have to do a lot of work here because we know that sine of h over h is an even function. What does that mean? Well, let's review. That means that f of negative x is equal to f of x. If we were to substitute negative x here for sine negative x here, sine negative x is equal to negative sine x over negative x. And then negatives would divide out. We're left with sine x over x. So since this is an even function, that means it's symmetric across the y-axis. And that means as h approaches 0 from the negative side, sine h over h also equals 1. So we can say that the two-sided limit of sine h over h is equal to 1. This is going to be a very important idea for us. Now, I said there's a second important limit that we're going to look at. We're also going to look at the limit as h goes to 0 of cosine h minus 1 over h. And you'll see why these are important when we get into the differentiation. So, there's an identity the half-angle identity. It says that sine of theta over 2 is equal to 1 minus cosine theta all over 2 square rooted. And we would go with positive or negative. But I can rearrange that just a little bit and say that sine squared theta over 2 is equal to 1 minus cosine theta all over 2. And I can manipulate this further yet and say that cosine theta minus 1 is equal to negative 2 sine squared theta over 2. And you might be going, well, why in the world would you want to do that? I'll show you the usefulness in that, and you might be able to see it already where I'm going. But I can now substitute that for this, and I'm able to rewrite my limit statement. And you might be thinking, well, that makes it harder. That now you have squareds and over 2's, and well, that's actually okay. That's a good thing for me. And I forgot my 2, but that's actually okay because I can rewrite this yet again, do a little bit of algebraic manipulation. It's the same thing as having h over 2 in the denominator. What? Stay with me. This is equal to the opposite of the limit, and I'm going to rewrite this as h over 2 goes to 0. If h is approaching 0, h over 2 is also approaching 0. And I'm just going to do a little bit more manipulation. This is sine h over 2 over h over 2 times limit h goes to 0 of sine h over 2. So I split up the sine squared h over 2. And why do we do that? Well, this limit, we just saw what that's equal to. We know that that limit, if we were to replace this with an h instead of the h over 2's, that's equal to 1. And we have the negative in front of it. Now what happens here as h goes to 0? As h goes to 0, we're getting closer and closer and closer to, well, 0 divided by 2 is 0. Sine of 0, what's sine of 0? Sine of 0 is 0. So as h approaches 0, we do a direct substitution, find that this is 0, so this limit that I started with is equal to 0. So keep these two things in mind as we develop the ideas for differentiation with trigonometry. And here we go. We want the derivative of sine x with respect to x by first principles. Ooh, first principles, what was that? Well, that said that f prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x all over h. Remember this thing? It's the definition of our derivative. So, if I want this derivative, I need to do limit h goes to 0, sine x plus h minus sine x all over h. And now we have to do some expansion. We use the sum identity for the sine function. And if we expand that out, we get sine x cosine h plus cosine x sine h minus sine x. And this is all over h. We see that this term and that term both have sine x. I'm going to go ahead and factor that out. What we're left with is cosine h minus 1 over h. And we're also adding limit h goes to 0 of cosine x times sine h over h. And I've done a little bit of rearranging, and I've split this limit into two separate limits. But the beautiful, crazy cool thing is, we know that the limit as h goes to 0 of this part in parentheses, that's 0. And we know this limit is equal to 1. And remember, sine of x doesn't care what h does because it doesn't have an h. So this expression has now become sine x times 0 plus cosine x times 1. So the derivative with respect to x of sine x is equal to cosine of x. There we have it. And we could go through a similar derivation for cosine, but I'm just going to give that one to you as a challenge. Why don't you try to derive it? But the derivative of cosine x with respect to x is opposite sine x. So these two things, very important for everything that we're going to do throughout this unit.